This is the new Arduino UNO Q. It combines a Qualcomm Dragonwing QRB2210 microprocessor and an STM32U585 microcontroller. Both of these are quite powerful, which turns the UNO Q into an interesting hybrid of single-board computer and an Arduino-style microcontroller. Because of this, I kept getting the question,
why would I use this over other single-board computers?
and that's a great question. In all honesty, I find that it struggles some if set up as a full computer with a monitor, keyboard, and mouse. It has a quad-core ARM Cortex-A53 running at 2 GHz and 2 or 4 GB of RAM along with Wi-Fi and Bluetooth. Right now, you have to use the single USB-C port to connect computer peripherals like a keyboard, mouse, monitor, and so on. However, there are a ton of GPIO pins on the back, including camera and display interfaces. A carrier board is supposedly in the works to break out some of these. It includes a Qualcomm Adreno GPU, so you can run some video processing or 3D rendering, but I found that the CPU actually performed better on most AI tasks. So again, what is it good for? In my opinion, it's quite promising for robotics. The lack of computer ports means the microprocessor side is better for headless applications that require heavy processing, like computer vision, AI, and web servers. The microcontroller side is perfect for real-time processing, like reading sensors and controlling servos. My hope is that we'll see a ROS port for the board soon, but until then, why don't we try making a simple robot that incorporates some computer vision and machine learning? Let's jump in. Hey Jay, I'm working on demonstrating the Arduino UNO Q. I want to do something with robotics because I think it's a good fit, and I'm thinking about redoing that face tracking robot or that pan tilt head that you and I did a while ago, doing something similar like that, but I kind of need your help to make it look decent. Do you think you could do that?
Sure, shouldn't be a problem. What are you thinking of designing it to look like? Is it going to be more for like characteristic, or you just want it to be functional, or?
Mostly functional right now, but I'm thinking the design of like Orbit's head where it's, kind of wide because I got a USB webcam. It's like one of the wide ones. And so just kind of move up and down like this would probably be perfect for this application. And then my hope is that you can take this idea and build on it in future robots if you want to add some interactivity.
Sure, I'm always looking for more interactivity. Sure, that shouldn't be a problem. Let's see what we got. Like, how heavy do you think the actual camera is going to be? Because we could power off of small metal gear servos, because those are really well working. Or we can do a type of gear movement. That way, the gears kind of slow it down and also take some of the weight off. So we can do either of those type of ideas.
Yeah, I trust you on how much you think those servos can push, but yeah, some basic hobby servos would work. I mean, metal gears are the way to go for this, I think, because the plastic ones I strip like crazy.
Yeah, definitely want to go metal when it comes to something like this. Plus, this is going to be the first time seeing the Arduino Q doing some cool stuff, so I'm excited for that.
Thanks to Jay's efforts, I'll go ahead and 3D print the pan tilt mount. Note that all the STL files and code will be available in a GitHub repository should you want to recreate the project or modify it for your own uses. I've gone ahead and put everything together. It uses two small hobby servos, one for pan and one for tilt. The USB webcam sits inside the top, and I put a translucent diffuser over the LED ring. I also wired up everything to the UNO Q. Pins 9 and 10 control the servos, and pin 4 controls the LED ring. I've added a few hundred microfarad capacitors across the power pins on the servos in the hopes of reducing jitter. These hobby servos are prone to that, so a future update might be to use better servos. I want to do a little more than track faces, as that's been done plenty of times, even without machine learning. I absolutely loved Cyril Engman's talk at SuperCon. He built LuxoPi, a fully interactive lamp inspired by Pixar's iconic Luxo Jr. Part of it included face expression recognition. And by that, I mean the lamp would recognize faces and attempt to classify the emotion based on the expression it was seeing. It would react to faces that seemed happy or sad or angry or surprised and so on. Let's take Jay's pan tilt design and make it track and respond to human facial expressions. To do that, we'll need to train a machine learning model that runs on the microprocessor on the UNO Q. We'll have it send coordinates to the microcontroller that controls the servos and LED ring. You Only Look Once, or YOLO, is a family of object detection models maintained by Ultralytics. They've been around for a few years, and they work great as off-the-shelf models pre-trained on the COCO dataset. Generally, the newer versions of YOLO work better than older versions, but you sometimes run into issues with certain operations in the model not being supported by your target runtime environment, like ONNX runtime. So it's always good to check to see if the model works before retraining it. Because we'll be using ONNX runtime in a Linux environment, we can assume that newer models will generally work just fine. So we'll go with YOLO V11. There's also several sizes: nano, small, medium, large, and extra large. They have increasing numbers of parameters, but also generally increase in accuracy, at least on a set of test images from the COCO dataset. Because we're running on a low-power CPU, we'll want to use the nano version to keep things as fast as possible. Just note that it will likely reduce the accuracy. Ultralytics makes retraining the model very easy. They have a Python library, and you can just download a model pre-trained on the COCO dataset right from their site. Transfer learning is a machine learning technique where a model previously trained for one task is reused as the starting point for a new similar task. And that's exactly what we're going to do with YOLO V11, at least our nano version. As the COCO dataset includes person as a class, we should be able to retrain a model to something similar, like faces. I highly recommend capturing and labeling the data yourself, as it will help train the model to work with your face, your expressions, and in your particular environment. But as a quick test, we can use someone else's data. That saves us a ton of effort. RoboFlow has a lot of great pre-made datasets available for free. Note that you'll need to create an account to download them. If you go to Products Universe, you can search through various datasets and models. Let's search for face expression and filter for projects with at least 1 star, so we know that others have at least maybe tried it. We'll go with this project. Note that it has some models pre-trained on the data, but it looks like it's the small version of YOLO V8, which is still too big for our use case. So we'll need to download the dataset. YOLO maintains a popular format for labeling bounding boxes, so let's go with that for the dataset. V8 or V11 should work. If you follow the directions in the GitHub repository, it will walk you through building and running the Docker image so that you can run Jupyter Lab in a browser. Once you fire that up, you can go into Notebooks and open up Training. This is the notebook we'll be using to retrain the YOLO model. So if you click on the first cell, you can press Shift-Enter to run it. That will just import a bunch of libraries for us. So keep pressing Shift-Enter and following any directions here. Notice that the script will automatically download or output some files for you, which you can set up here, such as the output model. I'm going to keep pressing Shift-Enter to get through this. There's a manual step where you need to download the human face expression recognition dataset that we just looked at. You have to do this manually because RoboFlow changes their API key every 24 hours, so even if I gave you one here, that will ultimately change because it's based on your account. So you could set up something where it downloads automatically, where you log in and it downloads, but to make it easier, I'm just going to say download it manually, and you need to unzip that into dataset. And this is the data that comes out of that. Notice that it is in YOLO format, which is what this script expects. I'm going to skip this cell because it's already been extracted for us. But I am going to run this cell where it loads the dataset metadata, such as the location of the training, validation, and test images, number of classes, and you can see the different expressions we have here. Next, we'll download the model weights. This is the model itself. The weights have been pre-trained on COCO. And then in transfer learning, I'm going to enable TensorBoard logging. And then this is the actual training step where we run this model.train because the model has been loaded using this YOLO function where we give it the path of the model, which we put into models. Here we have YOLO pre-trained. So if you see how we downloaded that, that goes into this pre-trained model path. That's going to open it. YOLO comes from the Ultralytics library, which is right here. And that's going to handle in one step, freezing the layers for us, training for a number of epochs or epochs, however you'd like to pronounce it. We set the learning rates. We will set some regularization to help with training. We will also tell it to do some data augmentation and set up some other hyperparameters so that hopefully this converges and we can actually train on that data set we downloaded. So when I shift enter on this, it should load up the model, start feeding it some data. You can see it freezing the layers in the YOLO model. And it's working through them, setting it up, and it should start training in just a second. There we go. I've set up Ultralytics to log metrics to TensorBoard, which we can browse to in a separate tab. We'll let the first part train for a while. Remember that we are only retraining the last few layers here, which are used to identify the facial expressions. Once that training is done, feel free to look through all of the output. You can see the different epochs here. Feel free to check out the mean average precision. These are usually good numbers to tell you about how accurate the model is, going up to 1.0, which is 100% accuracy. Anything over 0.5 is pretty solid, but I would use this 50 to 95, which gives you percentage of overlap of the predicted bounding box versus the ground truth bounding box. Ideally, that number should be going up, but as you can see, it maxes out around 0.43 or 0.45. This is where we load the best one from that previous run. We are going to unfreeze all of the layers, so we have no frozen layers. Ideally, you want to lower the learning rate. These don't seem to be affecting it because I think there's a different learning schedule going on in the back end and I didn't dig into it yet. But we're essentially using much of the same to retrain it and allow the model to pick up on some of those earlier embeddings that happen in those first few layers so that it's better at ideally picking up faces rather than what it was trained for on all of the Cocoa objects. So let's go ahead and start that. It's going to create another run for us, which means we can jump on over to TensorBoard and wait for that to update. Here, you can see the model learning a little more now that all the layers can update their parameters. We should be able to get a little better accuracy than had we just retrained the last few layers. Once the model is done training, it's always a good idea to test it. We're going to load the best model from that previous training step, and then we're going to run the holdout test dataset through it. So we will let that run. That's going to load all of those images in, classify them or perform object detection, and get us a mean average precision with either 50% overlap or more than 50% overlap of the predicted box versus the ground truth box. 0.5 is not too bad for a MAP of 50. Ideally, we want to see a higher MAP be over that. The important thing to note here is that it performs better with some classes, in this case like fear, happy, and it's going to struggle with things like angry, sad, and so on. Once we're done, we can print those metrics. We can convert the model. Note that we have the option of adding non-maximum suppression, NMS, or not. ONNX runtime by default supports NMS, but sometimes you will run into runtime environments where NMS is not supported. So we can disable NMS being exported with the model here. What NMS does is the output of the model is actually a bunch of anchor points in the image, and each anchor point might have more than one box associated with it, so you might get multiple detections per object, and non-maximum suppression looks at the overlap of all of those boxes and determines which one gives you the best score, and it returns only one. So ideally, you only get one bounding box per detected object when you include NMS. If not, if you don't include NMS, you're going to have to probably write it yourself. Otherwise, you will assume that you're going to have multiple detections per object. So I'm going to export it twice, once without NMS, and this will just be model.ONNX when it's saved to a file. And we are exporting to the ONNX format, which is an open standard that's shared among various different machine learning platforms. We will also export with NMS attached to that ONNX model. And now that we have the ONNX model, I'd like to test it using ONNX runtime because that's what we're going to be doing on the Arduino UNO Q once we deploy this model to the board. But in order for that to work, we actually need to pre-process the images manually. The Ultralytics library handled that for us when we were training the model, but when we go just to perform inference on the board, we will have to pre-process the image manually. That means loading the image, attaching letterboxes, which are black bars, in order to make the image square, and then resizing it to that 416 by 416 resolution, which is what the model now expects because that's how we trained it. That's a good trade-off between being able to detect far away faces and having decent speed, more than like 2 frames a second, on the Arduino UNO Q, and that just takes some experimentation. So that's what this pre-process image does, and we will reuse this function in our Python code on the UNO Q. We also want to be able to scale the bounding boxes to match what the model expects. Most of this is just for testing right now. We can scale the bounding boxes back to the original if we want to display the image. Note that bounding box information generally comes in the form of top left corner, so x1, y1, bottom right corner, x2, y2. But when dealing with YOLO, it actually prints out the class. Sometimes you'll get a score with that. The center of the box, which is x and y, and the width and height of the box. So this allows us to translate from a traditional bounding box format to what YOLO expects. And then we can convert the image to a NumPy array. And here's a helper function in order to display the image using matplotlib. So now we load up a single image from the test set here. We're going to show it. These are the ground truth labels that it finds all of the faces and associated emotions with those. Notice that this image is square. So when we go to pre-process it, it's just going to resize it from, I think this is 640 by 640 to 416 by 416. And it does not need any letterboxing because it already comes square. Now we're going to pre-process the image. So you can see the text is now bigger because we reduced the size of the image. We will load the ONNX model. Notice we are using the one with NMS. We're going to load the image, and then we're going to run inference. We need to convert the bounding boxes from the inference we got here back to the original scaling. We need to convert the bounding box to the YOLO format, and then finally we can visualize the inference results here. So it finds the faces just fine. However, you will probably notice that it struggles a little bit with some of the classes, so they probably don't exactly match up. Once you are happy with the results of your model, we are ready to deploy it to our Arduino board. All right, let's take a look at the code that's going to go on the UNO Q. If we go into firmware, there is the face detection robot. Here we've copied in the model with nms.onnx. That will run with non-maximum suppression. Let's go into our Python code. And if we scroll up to the top, you can see we're using ONNX runtime as our inference engine. We set some parameters here. And notice that we copy in the class names that we get from the data set that we downloaded. We have a data class to hold our inference results. We have that pre-process image that we copied in from the notebook. Once again, we probably need to convert the image to NumPy. We can draw bounding boxes so that we can display the image on the web UI. And then we can get the largest detection because if there are multiple faces in the image, we will want to just get one of them to have the robot look at that one. In this case, we're just going to find the one with the greatest area, assuming that's probably the closest face. We're going to create a custom class here, and we're going to run a thread that handles inference and updating the web UI. So we initialize everything here. We start the thread running right here. We can stop the thread if we want. So here's the main inference loop. So once the thread starts, this loop is what's run. We capture a frame from the webcam. We perform that pre-processing where we letterbox it and scale it as needed to that 416 by 416. We convert it to NumPy, and then we perform inference by calling this self.session.run. That's the ONNX runtime environment. We give it the NumPy image. It says batched here, but in reality, it's a batch of 1. We will get the detections that come out of that, and then we shove it all into that result object. From there, that result object can be used to animate the head, which is a separate function, as well as update the web UI if we have that enabled. And then we do some cleanup here. This is me trying to prevent some memory leaks that was going on. You probably don't need all of this, so feel free to play with the garbage collection here. You will find that running this takes up pretty much all of your processing power on the UNO Q to where all 4 cores are maxed out. So just a heads up on that, this is very processing intensive. In animate head, all we're going to do is get the X and Y norms. So that's just normalized X and Y. So the image, instead of being pixels, goes from 0 to 1, where 0.5 is the center. And so this is the location of the bounding box. It's the center of the bounding box, and we send that information off to the microcontroller side using this Arduino bridge library. So we just say bridge.call animate head. On the MCU side, we need to register a function with this name, and this passes in the parameters of the X and Y norm, the class associated with that largest bounding box, and a score in case we want to do something with that confidence score. We have a web UI. This is something I borrowed from the Edge Impulse examples that came with AppLab on the UNO Q, where we're just going to continuously update an image using socket.io so we can see what the robot sees on a web page. Note that this can be a little slow sometimes. I haven't quite fully figured out when it slows down, but it seems to be related to the fact that this is running so fast and inference takes up pretty much all of the processing power. So updating the web UI sometimes isn't a high priority, and that can slow down. If you figure out how to make that work a little better, please let me know in the comments. I'm going to add a space here. And this is just where we fire up the script. So web UI is a library. It's one of the bricks that comes with the UNO Q. We're going to fire up our thread. This is the custom class we created. We're going to start it, and then app.run needs to be called because this is what runs, I believe it runs in the foreground, which is why we're doing inference as a separate thread. This runs all of the bricks that we loaded, like the web UI. So you have to call this because it runs things like the web UI along with that bridge. Let's take a look at the web page briefly. So we have a very basic page that's just going to show us a video container, and then it gives us some stats about how fast it's performing inference and things like a frames per second counter. In the JavaScript, all we're doing here is initializing socket.io, and then pretty much anytime we get an image from the Python script, it's just going to refresh the page with that. And then basic error handling, and then we also have the ability to update stats to figure out how fast inference is being performed. Okay, so we've got all that running on the UNO Q, and that's on the microprocessor side. If we go into Sketch, we can see sketch.ino. This is the Arduino sketch. There's a lot of experimentation going on in here with things like PID loops to try to make the head move a little more smoothly. I could probably simplify a lot of this, but it seems to be working well enough for now. I had to put together a very quick NeoPixel bit banging library, and this is it right here. We're getting the address of the GPIO port, and notice you have to do a little bit of research to figure out which pin it's connected to. So we're going to be using D4. It's hard-coded in here. We initialize that pin as output, and then we run this macro to turn it high or low. And you can see here we're doing direct reads and writes to the register. There's no NeoPixel library for the UNO Q yet. That's supposedly coming, but for now we're just going to bit bang this and rely on the very fast speed of the STM32 in order to drive those NeoPixels. I wouldn't try driving more than maybe 10 or 20 NeoPixels, but this is good enough for our little 12-pixel ring. Okay, back to our main code, which was sketch.io. We have some settings here. These are the patterns. They're statically encoded. So for example, angry, just the sides turn red. Disgust, sides turn green. We've got fear. The smiley is supposed to be kind of yellow. It comes out kind of greenish. I should adjust these, but it kind of makes a little smiley face. It says line, but really it's just the left and right pixels, left and right of the camera for neutral face. Frowny ends up being blue. It's supposed to make a little frowny face above the camera. Surprise is full magenta, and then we can clear the LEDs. So in our functions, we have our simple PID controller. That allows us to create a little bit of a smooth motion when we're trying to track a face, when we get the X and Y coordinates from the Python side. I tried to create a very simple filter that records the last 3 expressions detected. And if 2 or 3 of those are one expression, that's what is used to update the LED ring. So that way it's not flashing back and forth if it's getting multiple detections very quickly. It actually waits a moment before it's sure to give you that expression result. We can set the LED pattern here just by copying in the static pattern into the frame buffer. Then we have this animate head function, which is a callback. So whenever the Python side says call animate head, we've registered this function will get called. It attempts to track the X and Y error on the frame, and then later we will convert that to servo movements. So it tries to center the camera so that the face, the bounding box, or the center of the bounding box is in the center of the frame. And it saves that information. So this is tracking X and this is tracking Y. So it saves them as target camera angles that we want to track to. We update this expression history. That's the last 3 expressions that were saved. And then we update the LED pattern if 2 or 3 of those expressions are in the history. And then we take some timestamps to use for things like debugging and seeing how fast this takes to run. In setup, we just initialize everything. And then in loop, here's where that target angle comes into play for both X and Y. So we get this offset, and we use the PID loop to figure out the error, to track that error. Once we know that, we create a velocity profile so that the movement starts off pretty quickly and then decays exponentially. So over a few frames or updates, it will start fast and then slow and then move fast. So it seems a little jerky at first, but it's kind of similar to how a real head moves, or something like your eyes. We do that for both X and Y. Once we have that offset error and how fast we want to be moving from that velocity profile, we then translate the camera angle, what we think the camera angle is, into actual servo movements. And we use those servo movements to write to the servos to actually move the pan tilt mount. The other thing we want to do is, if we haven't seen a face in a while, in this case I think it's 2 seconds, go ahead and turn off the LEDs so it's not just sitting there with the lights on from the last detected face. And then we want to wait before the next update. I think I'm aiming for about 20 updates per second here. With that done, we are ready to upload this to the board. If you notice, I'm doing all of this work outside of App Lab because I want to do it locally on my computer so I can keep it under version control with like Git. So we're going to take our code and we're going to upload it to the Arduino UNO Q using SSH or SCP. Let me go ahead and make sure my work is saved. I'm going to go to View. Let's go to Terminal. It looks like I still have Jupyter Notebook running, or Jupyter Lab. Let's Control C to shut that down. Notice that I'm in Windows Subsystem for Linux. PowerShell might have a version, but definitely don't use Command Prompt if you're using Windows. because we want access to the SCP command. Make sure you are in the face expression detection robot repository or folder here. I'm going to use SCP, R for recursive. Let's go into firmware. We want the face detection robot, and we want everything in there. That includes the assets, which is the website, the Python script, the sketch, the project metadata that's in app.yaml, and definitely the model. We're going to send that to the Arduino user at 10.0.0.80. That's the IP address of my UNO Q. That will probably be different for you. And we're going to send that to the home directory, Arduino apps. That should be one word here. And that's a directory that's set up for us on the UNO Q. It'll ask you for your password. Let that copy. Once it's done, that means all of our code is now on the Arduino UNO Q. Let's SSH into it. I'm going to use PuTTY because I'm on Windows, but feel free to use whatever SSH client you want. Arduino should be the default username, and then type in the password that you set up. I recommend running AppLab at least once just to update the firmware and to configure the UNO Q with things like Wi-Fi and giving it a new password. To run the app, we're going to use Arduino app CLI, the app subcommand, and then under that, we're going to say start. And then we're going to tell it where that app is located, which should be Arduino app's face detection robot. We're going to fire this up. It might take a few minutes the first time you run this to install all the dependencies. Once it starts running, you'll hear the servos move to their default positions. And then we can browse to the website being broadcast from this, which for me is at 10.0.0.80 and port 7000. Now, let's see if it's working. I'll come into frame and make a face. It captures surprise. Let's try smiling. Oh, it gets happy and it tracks me. All right, neutral. There we go. It struggles a bit with that. Angry? No. It's not really finding that. Sad? Yeah, it just thinks it's happy. And what was the other one? Something like fear or disgust. No, it just thinks it's happy. Okay, so it's struggling, but surprise and happy it does just fine with. And it seems that lighting is very important for this. I can be a little closer. There we go. It's tracking me. Once you're done, you can type Arduino app CLI app stop, and we'll say we want to stop the face detection robot application. You'll notice that it will gracefully stop here, exit out of everything, stop broadcasting that web page. And we can also look at the logs. So all of those print statements on the Python side get logged to this log system where we can say Arduino app CLI app logs and then give it the location of the app, and it will print out the logs. These are all the print statements from the Python script. AppLab has a serial monitor so that you can watch all of the serial.print, or actually I think it's serial.monitor statements in the Arduino code. In theory, we should have something similar with the CLI interface here, where we have Arduino app CLI app monitor, and then we can give it the location of our app. But when I run this, you see I get an error. Even if the app was running, I still get this same error because it says panic not implemented. I think this is a coming soon feature, so we don't have a serial monitor right now for the command line interface if we SSH in. For debugging the Arduino sketch, I recommend using a USB to serial converter connected to pins 0 and 1. That way you can use serial.print statements in your code. The model is far from perfect, as it fails to detect a number of classes in my environment and, well, on my face. You'd want to collect a bunch of data for your particular use case, such as your face in various environments, and then retrain the model with the new images. However, this should be a good starting point for building a face tracking and expression recognition robot. I'll make sure there's a link in the description to my GitHub repository containing all the code should you want to recreate the project or take it further. Good luck and happy hacking!